Hello everyone, this is going to be section 2.6 part 3, and we're going to check here the difference between infinite limits and limits at infinite. So first, let's recall what is a limit that go to infinity versus a limit at infinity. So in the case of a limit at infinity, we mean that we're taking the limit when x goes to infinity of certain function. And we say that a limit is infinity or go to infinity if when you compute the limit, you're obtaining an infinity, which is essentially what we got on the previous section. So to simplify both, we can use the function tangent of x in the inverse. Notice that the function tangent of x, given here by the black line, it goes to infinity when we're approaching pi half, and approaches minus infinity when we're approaching minus pi half. So in both cases, these are limits that go to infinity. Okay? And this goes to infinity, this goes to minus infinity. Now, because we can also take the inverse of this function, minus pi half to pi half, we can talk about the arccotangent, or the tangent to the minus 1. And if we take the limit when x goes to infinity of tangent to the minus 1, of x, that's actually going to send us back to pi half. And in this case, if I take the limit when x goes to minus infinity of tangent to the minus 1, this is going to take us to minus pi half. So it's going to bring us back to the original point that produced the infinity for the tangent. So you can see now here the difference in those. These are limits at infinity, and these are limits that go to infinity. Okay, so in this section we're going to focus more on the limits that and the limits at infinity. So we're going to take a limit when x goes to infinity or when x goes to minus infinity. Okay, so let's see the definition of this and the notion of horizontal asymptotes. So if f of x, or function, becomes arbitrarily close to a finite number L for all sufficiently large and positive x, so we're meaning when our x is bigger than a very large number and our function is approaching L, a number L, we can say that the limit when x goes to infinity of f of x is L. Okay. In this case, this line y equals L is what is called an horizontal asymptote. The vertical asymptotes, remember we saw that in the previous sections, is when we have problems in the domain, so the zeros of a rational function or that kind of thing. In this case, what happened is that when we take a limit to infinity, we get a finite number. That finite number, that line in y is going to be horizontal asymptotes. And horizontals are a line that goes like this in the y-axis. Vertical, there you go like this. Okay? So just the difference between the two things. Similarly, if the limit at negative infinity is some number m, we can define that analogously and say, well, if the limit is this, y equals m is an horizontal asymptote. So now let's take a look to an example of what I'm just saying. So I'm going to take this function here, which is f, and it turns out that when I go very far, x go to infinity, the function is going to make this. It's going to approach the line L. It doesn't necessarily have to touch L. Remember that this is a limit, so it doesn't necessarily have to touch the point. You just got to approach a lot to it. Every time that we move more, it approaches more L. So if I take, let's say, x equals 1,000,000, is closer to L. But if I take 30 millions, it's going to be much more closer to L than before. Similarly here, when I go to minus infinity, if I go to minus infinity in this direction, then the function is going to be approaching the line m and y, and we can say that the limit when x goes to minus infinity is m. And the larger negative numbers that we take, the more is going to approach m. Now, this is clear from a graphical point of view. But sometimes it makes a lot of sense if we mirror it with the rule of the function. So in this case, we're going to take the function f of x equals 2 plus 10 over x squared. Notice that this is a function that is going to have both vertical and horizontal asymptotes. Notice that the vertical asymptote is clearly at 0 because this function has an issue at 0. It's not defined at 0. So it's going to have this wide vertical asymptotes. And when you get closer to 0, this is going to go to infinity but both sides. So the limits, the limit at 0 goes to infinity. And so that's in terms of vertical asymptote. But the horizontal asymptote is also going to happen in this function. Notice that when we go to infinity, this value here in x squared is going to become really large. So if I take 1,000,000 here, then 1,000,000 squared is going to be a super large number, and 10 divided 1,000,000 is going to be something really, really close to 0. So that means that it doesn't matter if I'm approaching a large number on the positive number or a large number in the negative numbers. This quantity here is going to be, every time that I go further, much more closer to 0. So when we have something like a constant divided by a growing amount, that is going to go to 0. And this is the type of behavior that we're going to see in general with most of the limit at infinity. We want to check who's growing faster, the top or the bottom. If the top is growing faster, then it probably is going to go to infinity first. But if the bottom is going faster, then this quotient is likely going to go to 0. Okay? So in this case, yeah, this goes to 0, gets closer and closer to 0 the more than we go, and the limit in both cases to infinity and to minus infinity goes to 2. Now, let's take a look to another example. In this case, I have the function f of x equals 5 plus sine of x over square root of x. Okay? So in this case, y equals 5 is going to be the horizontal asymptote of this scenario. And when we're going to infinity, this sine of x over square root of x is going to go to 0. Why is that the case? Well, remember that sine is a bounded quantity. Sine is between -1 and 1. So this, the sine of x, it doesn't matter where we are. If we're in a very large number, this is still going to be a number between -1 and 1. So a number between -1 and 1 versus something in the bottom that is growing really, really fast to infinity means that this little piece is going to go to 0. Okay? And so when we're approaching infinity, this whole function is going to be approaching 5. And that's why 5 becomes here a horizontal asymptote. Now, let's talk about infinite limit at infinity. So we talked about infinite limits before, but when we were approaching a given function, a given number, right? So we were saying, well, when x goes to 0, that the function is going to infinity or to minus infinity. But it can happen as well that when you're approaching infinity, the function is just going to go to infinity. Especially that can happen if you have things like you don't have a rational function, but you have a function like x squared or any line or an exponential. Anything that is that it doesn't have something suppressing the growth of the function is going to go to infinity. Okay? So if f becomes arbitrarily large, as x is becoming arbitrarily large, then we can say that the limit when x goes to infinity of f of x is going to be infinity. And similarly, we can define the limits for minus infinity and the limit when x goes to infinity of f of x being minus infinity, or the limit when x goes to minus infinity of f of x being infinity, or the limit when x goes to minus infinity of f of x being minus infinity. You can define all this similarly. Essentially, we're going, as x is becoming large in the positive direction, it becomes super large but negative in sign, then it goes to minus infinity. if it's becoming increasing, if x is large but negative, and f of x becomes large, then it goes to infinity. If x is becoming large but negative in sign, and f of x also becomes large but negative in sign, we can think of it as going to minus infinity. Okay, so just to take a look at an example of that, consider the function f of x equals x cubed. Notice there's nothing hampering the growth of this function. When x large, then x cubed is going to become large. There's nothing that is saying this is going to be reducing. So if this grows, if x grows, x cubed is going to grow. And in this direction, when x goes to infinity, then x cubed goes to infinity. And in the opposite direction, if I take a negative number, so if the negative number is large, minus a million cubed is something super large and negative as well. So this is going to go to minus infinity. Now, in general, the powers, the powers, they have behaviors that we can classify. If n is an even power, so x to the square, x to the 4, x to the 6, they have this kind of behavior. And so you can see clearly the behavior at infinity. So in a power that is even, the limit when it goes to positive or negative infinity is just going to produce an infinity. Okay? If n is an odd power, then it differs. If n is odd, then if it goes to infinity, is infinity. If it goes to minus infinity, is minus infinity. Okay? And the example of the odd powers, x to the 3, x to the 5, x to the 7. Now, an example of this with a more complicated function will be the polynomial. So in a polynomial, you can have a mix of positive and negative numbers together with even and odd powers. And it just is going to depend of each polynomial, the numbers that you're going to be approaching. So for example, in this case, we have minus 2x cubed plus 3x squared minus 12. Turns out that if I move to larger numbers, to large number positives, like 1 million, 2 million, 30 million, then it turns out that this is going to actually become negative, and it's going to go to minus infinity. You can see that here. But if I take a large negative number, minus 1 million, minus 30 million, then this is actually going to become a positive number. And so this polynomial is going to go to infinity.